Welcome back. All right. Next up, we have Augmenting osquery Visibility on Windows through Reverse Engineering. Welcome, Guillaume Ross and Marcos Oviedo, and take it away.
Hey, thank you very much. This is Guillaume. Just by the way, I'm not able to enable the video on the Zoom, but you've got the slides, so I think this will work really great. So Marcos is driving the slides, and there's going to be a lot of live demos in there, so it should be pretty interesting. So today we're going to talk about how we augmented visibility on Windows for osquery. And we will start by talking a little bit about the two of us, what Fleet and osquery are for those that are not familiar, what you can do with operating system configuration data, what Windows has in terms of that type of security configuration data. And then Marcos will take you through how we reverse engineered some built-in Windows tools so that we could understand some internal APIs that are undocumented, all the way through contributing back to the open source osquery project so the visibility could be augmented for everyone that uses it. All right, so I'm going to let Marcos introduce himself. Are you muted, Marcos?
Yeah, sorry. Thank you, everyone. Thank you, Guillaume, for the introduction. I am Marcos Oviedo. I am a software engineer at Fleet. And I define myself as an InfoSec nerd. InfoSec has really been my passion for the last 15 years. And during that time, something that I found that I really enjoyed doing was to contribute back to the community, to either to enhance a current tool or create new ones. And as a little fact about me, I was part of the team that organized the first B-Sides edition back in my hometown in 2019. That was B-Sides Cordoba, Argentina.
And I'm Guillaume. I'm the head of security at Fleet. I've been doing security for a long time. Also been using osquery for a pretty long time. And what I like to do is leverage compliance to improve actual security, right? Like instead of just checking a checkbox somewhere, just making sure we're improving things. And I'm in Montreal. So of course, by law, I am required to like hockey and poutine. And funny enough, I work with Marcos now. He's in Argentina. I'm in Montreal. So, you know, we're pretty much on top and bottom of the Americas. And InfoSec is such a small world that we realize we have some common friends and ex-colleagues last week. So Marcos is going to be doing most of the talking. And I actually almost feel bad that my name is on the talk because I was just someone who needed something to happen. And he's the one who actually did it. So if you can switch to the next slide, I'll talk a little bit about osquery and Fleet. We're not going to talk too long about it. I assume many of you are familiar with it. If you're not, osquery is essentially an endpoint agent that makes your endpoints, they could be servers, workstations, Mac OS, Linux, and Windows, look like a relational database, right? So if you want to know what users exist on a machine, well, there's a table with a list of users. What processes are running? Well, there's a table with a list of every process that's running. So it's very powerful for things that are related to like threat hunting, but it's also really good for tracking the configuration of systems to be sure that it is as you expect. And it's really lightweight. Now, Fleet is also open source. So we're essentially in the middle in this diagram here. So you see osquery is on the left. That's the endpoint agent. And you can configure it from Fleet. You can schedule queries that happen on the osquery side from Fleet. And then the data will go back to your Fleet server where you can then forward it to your SIM, store it in the S3 bucket, send it to Splunk or whatever. And everything in Fleet is also available via APIs. So we have a Fleet Cuddle, which is like a command line tool to do pretty much anything you want with Fleet and osquery, right? So if you need to know something about a machine while using our tools and our API, you can query these machines live or, you know, at a scheduled frequency, including something that we call policies. So there's close to 300 tables in osquery. Got a little video playing here. I'm selecting star from the users table on my own laptop. And oh, thanks for increasing the resolution. So you'll see it's going to take like a couple seconds. And what happens is the Fleet server sends the query to osquery on my Mac, and then you can see my user account is in /users/G, right? I could do the same thing and select from processes, where processes are not stored on the drive, right? So if you have something that's running and is only in memory and is not on the drive, then you would get results, right? Like, I hope there's nothing like that on my laptop right now. Yeah, as you can see, it's responded and there's no data, so we're good. So I think it's 275 core tables now. Some of them work on all operating systems, and some of them are operating system specific. So for example, on Windows, there's a registry table you can query. Obviously, that doesn't exist on macOS or on Linux. So the usefulness of configuration data that you can get through osquery is essentially to enforce and track security hygiene, either for security purposes or it could be compliance. So we've got a feature in Fleet that's got that we call policies, and they're essentially queries that pass or fail, right? So the example you see on the right, that's one that we use internally, where I'm checking that we all use Macs, and we're just checking that File Vault is enabled on all of our Macs. And then if it's not, the policy will fail. And then we can send that to like a Jira ticket, ServiceNow, or what we actually do is we route it through a SOAR with webhooks, and then we send it to our Slack to tell someone like, okay, what are you doing? How is File Vault disabled, even though it's enforced with MDM? But there's a lot of these settings that you want to track to be sure that things are configured as expected. And so Fleet is cross-platform, but then these tables are different on all different operating systems. So on the next slide, you can see here we're Mac first, right? So we've got, these are all the policies that we actually run on our own laptops, right? So things like, are people storing SSH keys that are unencrypted on their laptops? Is Google Chrome up to date? Is the drive encrypted? Like all of these. And by the way, these are all open source. You can go on our website and find all of these queries. But there's a bunch of stuff in there that if we wanted to do with Windows, it's not that easy. So from the bottom, you've got one that was checking like the password policy, for example, that it requires 10 or more characters. On the Windows side, it's not that easy. So on macOS, there's a bunch of tables that use operating system APIs directly. And when you don't have a table with the data that you want, you can always check to see if your MDM is pushing the policy, right? So instead of checking, is X configured to Y, you can check, is there a profile that will configure X to Y, right? So it's a little bit disconnected from the end result, but lets you get a lot of visibility really quickly. On Linux, pretty much everything is a file. And there's a table called Augumenting in Linux that essentially lets you read a configuration file as if it was a table, right? So if you want to check your open SSH config to see if root logins are enabled or not, you would be able to do that with Augumenting. But then on Windows, a lot of these security configurations are in the registry, but not all of them. And even when they're in the registry, it's not always that clean or that simple. So,
okay,
yeah, so I'll hand it over to Marcos. Essentially, what I needed was a way of checking a lot more security configuration data from Windows in a reliable way. And that's where Marcos comes in with his awesomeness.
Thank you, Guillaume. So the problem was that we wanted to obtain information from the Windows security configuration policies. But first, we wanted to understand what these policies are and how they can actually be configured on Windows through the built-in tools. So we found that the security configuration policies are basically rules that can be used to enforce the security of a system. In particular, one can enforce the security aspect of different set of functionalities on Windows. We're going to see what those functionalities are. But first, we need to understand how these rules can be configured and extracted. So Guillaume mentioned that the rules are not exposed on the registry. So we found that the rules were actually manageable through something called GPO policies, and they can be locally configured through this local security policy editor, or a domain-wide, they can be configured through the group policy editor. And the rules basically contain a way to configure the password policies, account policies, local policies, and kernel policies. And we were mostly interested on the password policies aspect of things. We wanted to know what we can do with these policies. We wanted to understand what are the things that were exposed. And we found that by having this information, we are going to be able to create new and reliable policy queries, such as the one that Guillaume was showing a moment ago. So for example, we found that we can check for things like the minimum number of characters that a password should have. We can check for if things like if the guest account was disabled. We can check for properties of the password. We can check for even for audit information. So, you might be asking why we wanted to focus on password policy and why we wanted to have this type of information. And we decided that we know that the passwords are probably the most vulnerable component in an authentication scheme, and they are prone to different type of attacks. So, as a way to ensure how the password work, we wanted to have control on what was configured across our entire fleet. So let's break down the password policies a bit. So I mentioned briefly some of the characteristics that we were interested in, and we found that those properties were actually exposed through the password policies. We found that things like the minimum and maximum password age were properties that we can extract from these set of security configuration policies. We found that we can know that the password complexity requirements. We can know if the password is reversible on a system or not. And we also know we wanted I mean, another thing that was also exposed was the history of the password cache. So in the process of finding what these policies were and how the policies can be consumed, we found this tool called SEC8, which was a built-in tool that basically allow us to have information from the security policies and allow us to manage them and visualize them. So the tool is a command line tool, which is shipped together with the OS since Windows XP. And the tool allow you to expose these command line configuration commands. And we found that by calling the export option along with some specific security policies that we were interested in, we were able to obtain this information exported in a TXT file. So that was kind of revealing, because now we have a programmatic, I mean, we have a built-in utility that can give us this information. So we can, wrap up the utility with some code, some logic to execute the utility, return grab the returned data, and then parse that data so it can be presented to a different component. So by having this programmatic way of retrieving the information, we can automate the execution and run this functionality at scale over an entire fleet of devices. So that was the next step here. So we wanted to run this at scale. So the game plan for us was to call this SEC8 tool from osquery, then do the process of grabbing the data and exposing that data through a virtual osquery table, so it can be consumed by different tools such as Fleet. But in the process of doing this, we asked one of the co-creators of osquery, Zach Wasserman, who is happening to be the CTO of our company. So we asked him about this idea, but he mentioned that child processes or sub-processing in osquery was not desired. So we kind of stopped considering this idea as something that was a potential solution for this problem. And then we thought about the idea of actually creating some code that can behave like a SEC8. So creating the code that behaves like a secate will require that we will have to understand what secate does internally. We will have to understand which type of APIs are being called during the secate execution process. And we also have to understand that how to call these APIs. So the only way possible that we knew we can do this was through the use of reverse engineering techniques. So in order to mention how we end up doing this, we need to talk first about what reverse engineering actually does. So reverse engineering is the process of taking a binary file and understanding what it does. So that was kind of the case here. We have a closed binary file from Microsoft, which we don't have access to the source code. So we wanted to understand what this binary does. So reverse engineering was the way to go. So reverse engineering is usually used for analyzing closed source software, such as this case. But this is also used through a variety of use cases, such as vulnerability research, especially for binary analysis of new exploitation techniques, for example. It is used to analyze proprietary formats, for example, if media formats, if someone wants to be able to reproduce a new media format, and also for product verification and interoperability purposes. So there are, through this work, we use 4 types of reverse engineering tools. We use disassemblers, debuggers, decompilers, and binary format analyzers. So disassemblers are the tools that allow us to perform, to have access to a static view of the binary, to understand what were the assembly instructions being used in there, and to have an overall notion of how these assembler instructions were being called, what was the execution flow that was performed through the initialization parameters that we gave to the program. Then we use debuggers to actually perform a live inspection of the running binary in memory. So through debuggers, it can have access to the current state in memory of the program and inspect things like variables, CPU registers, inspect the state of the stack at any point in time and things like that. We're going to see in the demo how this real debugger works for this particular example. Then we have something called decompilers. Decompilers are basically functionality within debuggers and disassemblers that allow us to have a C-like representation of the assembly code. So it's a good way to understand at the very high level what a piece of code does, especially a function, what the function does. And the thing about the compilers is that they are not, they don't produce an exact output, a one-to-one output to the assembly code, because there are things that sometimes cannot be decompiled. But they do the best effort approach to give you an accurate representation of the assembly code. And then we have the binary format analyzers, which are the tools that allow us to understand the executable format. In this case, as we were working on Windows, the executable format that we wanted to analyze was the P executable format. So we use a tool specifically for that. The reverse engineering process can be performed by a variety of techniques that can be categorized on through something called static and dynamic analysis. So static analysis is the process of analyzing the binary without actually executing the binary. So one can use disassemblers for this work and have use the static view of the assembly code represent in the disassembler to take notes to understand the execution flow and know what are the things that we will expect to see when run the binary through the dynamic analysis process. Through the dynamic analysis process, what end up doing is to execute the binary and then step by step execute the program flow and see what are the things that are being call and use from within the code. Yeah, so this is a graphical view of what I just said. So when it comes to reverse engineering Secate, what we did was to first to understand what type of executable we had, and then what were the modules, or the also called DLLs, that this executable was calling. And then through a static analysis, we found a couple of interesting things that we then corroborated through dynamic analysis. And this was my first contribution to this problem. So I was asked to look for programmatic way to retrieve this information, and I found that Secate was a possible challenge to achieve that. But in order to confirm that, we actually had to do the work on reverse engineering, which is something that we are going to do in a moment. So after checking on Secate, and after I finding that there were some DLLs that were used across different components that were calling into this security configuration extension architecture, I decided to look into MSDN, into the Microsoft documentation, to have more information on this. And I found that the security configuration information was actually managed by this service called SCE. And that I found a couple of properties of the service, such as the fact that there were a client and a server component that were talking to each other and exchanging information that basically provides the policy that we needed. So so knowing that the components in action here, so we have secate.txt, and then we have two modules, SCE CLI.dll, and then SCE SRV.dll, which is the client and server components. Knowing that those were the main thing that I had to look for, I decided to jump and do the actual reverse engineering process. So, and this is the part that we jump into the reverse engineering demo. So let me stop this for a second. So we are going to start by looking into the Secate binary itself. So here I have this tool called PBeer, which is the tool in charge of performing the analysis of the executable binary. So we have a Secate open, and we have different properties of the Secate binary itself. The binary is as a standard binary that is present on the System32 folder. We showed a moment ago that how this binary can be executed. So we are going to see it now. So basically, the binary, if I call it from any place in system, it will be thanks to the variable path. It will be found on System32. So if I call the Secate binary with some specific arguments, we will see that the command executes successfully. And then if we open this output.txt, we'll see that the output, the policies output that we needed were present on the output of the binary. So things like the minimum password age, maximum password age, minimum password length, the password complexity, all of those things that I was briefly mentioning a moment ago can be extracted and consumed through this tool. So remember these command line arguments that I'm showing here. So we have export and areas. So those are the markers that we are going to look for in the reversed code to understand how these flags are being processed, and how we can use that to understand how this information is being obtained. Okay, so if we get back to here, we can see something important to mention, that there are a bunch of imports, static import information on the binary itself. And among those import information, there is this DLL that we happen to found that was the client component of the protocol that give us this data. And among the information that we can get here, we can also have access to the export of the functions that are being consumed by this library. So once we have this information, we jumped into the disassembler framework. So this assembly framework that I am showing here is called Realize. So Realize desktop is a tool, this assembly framework tool that has a freemium, free and a paid version. I am using the free version here. So basically, I started opening this second binary. I have some information on the binary itself here. And then if I go into the assembly view of the binary, it will show you, it's going to show me the entry point of the binary along with the different assembly instructions that are happening here. We can inspect things. We can inspect things such as the flow. So let me do, yeah. We can inspect things such as the flow of the execution flow of the binary. So we have the assembly instructions, but this time, whenever there is a potential branching interaction here, it is going to show different arrows to mark the possible options that the execution flow can take. And this is what we are seeing here. So we have all the execution flow of that entry point that we were seeing. And this is the compiled representation of the entry point, which is basically a function that performs some initialization for the program itself. And then after that initialization is done, it will end up calling the W main, which is the actual entry point of the program, because this entry point is basically a kind of a stub that the compiler adds to the binary in order to be able to execute the entry point of your actual code. So whenever you work on a C or C++ application, the entry point for your code is always main. So in this case, we see that this CRT startup function is basically preparing the execution context before calling W main. So if we jump into W main, we have these two variables that get received, which are basically the argument counter and the argument vector that contains the command line inputs. So if we go to the bit below on the actual compiled code, we will get to see that there are some comparisons being made against different tokens. So these tokens are basically the possible command line options that one can provide to this binary. I remember that we were interested on two of those options. We were interested on the export option, and we were interested on the, areas option, right? So we have the export option here, and then if we go down below, we have we should have over here the areas option, which in this case is so this code over here is comparing if the input argument was the areas/areas option, and then if that happens to be the case, it's going to end up setting up a flag to a specific value. So we are basically what we are going to do is to track where else this value is used to understand what this setting this value to a specific setting this variable to a specific value, what does is ended up allowing us to do. So if we check the areas parsing, then we also provide the security policy argument, which is going to set the variable in question to 1. Then if we will have provide a different value, a different argument, the different values will have been set to this variable. So as we provided security policy, the security policy flag variable was set to 1. So if we track the usage of that variable across our code base, we can see that this value is being set to this new variable called, in this case, is something that I remember. That's something that I forgot to mention. Sorry, that Once we have the compiled output of the binary, we can rename the different variables to a different name just to easily recognize what the variables are doing. So in this case, I renamed this one to final security policy flag. So if we again see where this variable is being used, we can find an interesting things such as this call in here, where the value is being passed as a flag. So yeah, we see that this function, which is called SC get security profile info, is using that flag with the value that was set through the command line option that we provide to secedit. Okay, so one more thing, really quick. So we mentioned that we also wanted to check on the export. On this export command line option. So the export command line option is being handled on the different on the else codes of this switch. So if we go to about this line, we can see that if the else part of that switch is being handled here, and that the flags export call is being set to a specific value, which in this case is 1. That is a spoiler that I have for you. So if go where the flag export is being compared to 1 within this code, the compilation, we can see that this if is being executed. So this is the actual logic that is going to be executed if we provide those specific values to secedit. So the logic is going to get over here. It's going to use the flag that was set thanks to the areas command line option, and then it's going to call this function. Okay, so we get to this point. Now we need to understand what this function actually does. So if we try to decompile that function also, we will get to see that the function is implemented in a different model, which is the model that we were looking for initially, the SCCLI.dll. So if we open this, we open through this assembler what this function is doing. So we will get the assembly code. We will get the execution flow of the function, and we also get the the compilation from the code itself. So among all other things, the function is parsing the data, and then it ends up using that data to call this function called NDR client call tree, which for those who don't know, which I guess it's maybe many, because this was something also new to me, was the call used to perform what is called the RPC client call. We are going to see what that means in a moment. But the overall idea is that this call gives you access to a specific protocol. So you can call functionalities from a protocol exposed internally by Windows and get response from that protocol. So this function was implemented again from a different DLL called RPC CRT4.dll. And the information from this call will end up being used by the get security profile to create data structure in memory and then return that data back to the caller. So the profile data that we need should be happening from calling this NDR client call and then executing some logic running a different process. Okay, so that's about it on the demo. So we have a clear path on how to reverse we have a clear path how to obtain this information. We need now to understand a couple of things before moving on, but at the very high level, we knew how to get the data. So the Windows IPC, so we briefly mentioned something about RPC things. So the Windows IPC mechanisms are really complex. So the Windows use different ways to communicate between the subsystems that are implemented by the OS. So on Windows, we have, as you know, we have services running that provides a different type of information. Usually those services expose their functionalities or the APIs the clients running on the system through an IPC mechanism called RPC. So RPC is basically a way to execute functionality running on a different process. Microsoft, this is something that Microsoft didn't invented. There was an standard around this called the DCE RPC. Microsoft ended up taking that standard and extending it to create the Microsoft RPC version. And the Microsoft RPC version is used by many subsystem Windows, from service libraries, different type of binaries. And there are a lot of custom protocols built on top of RPC. Being the Windows SE, or the security configuration extension, one of those protocols implemented on top of RPC. So from the code we saw, we get to find that the SE CLI.dll contains a RPC client that can speak into this protocol. And we also found that there is a DLL component that contains the information to understand these requests or these messages coming from the RPC client and be able to respond into those messages. And that is the server component for this protocol. So, so at this point, we either have two ways or two possible paths. We either go ahead and implement an RPC client from scratch. And by that, I meant we can, if we know how to speak this protocol, we can send this message request from osquery itself, and then wait for the response from the SE server. So that was one possibility, which was doable because there was a way to actually create the code required to implement an RPC client. But then we also found a second way, which was actually around using SE CLI.dll, the same way that osquery was using it. This was a way more simple approach, and also reduce the complexity, implementation complexity, and reduce also the risk of running with a protocol implementation that doesn't fully match the current and future changes to this protocol. So we want to go ahead and play safe and just use the SE CLI DLL and consume the DLL from the exported functionality in order to use that data. So if you remember, when we were checking on the demo, that were a bunch of exports on the DLL when we were using the P binary analyzer. Those exports are basically the functionalities that this DLL can export. But in order to call into that functionality, we needed to have a new trick in place, which was around using something called dynamic linking, which is basically a way to load DLL into a process and then retrieve the addresses of the function exported by that DLL in memory, retrieve those addresses so we can call into those addresses programmatically. So we wanted to have a piece of code that can do this logic of loading the DLL, getting the address to the exported function, and then calling to the exported function. So and that can be achieved through two API calls on Windows. First, we have the load library API call, which will be the one in charge of loading the DLL. And then we have the get proc address API call, which will be the one in charge of finding the address in memory of a given function. So this is some code that I put together here. We're going to see this working in a demo in a moment. But the overall idea is that by doing this, one can use some tricks in C++ to be able to call the function in memory using the exact signature of the function that was required for the signature to be able to receive the data in a proper way. So while we were doing this, we kind of wanted to have this working as soon as possible. So something that we did was to actually check for the usage of this function across the the entire GitHub code base. So we basically did a GitHub search, passing the name of this SE get security profile info function, which was a function that we found that was giving us this information. So after searching on GitHub, one of the only hit that we got from an actual implementation that we were using this function was a script, a PowerShell script from the NSA. So basically the NSA was using this same approach to get security compliance information, providing this security compliance information to a government agency. So they have an open source division on the NSA, which was publishing this PowerShell script doing this trick. So we were quite surprised about that, and that kind of validated that we were on the right track for this work. So okay, let's jump into this RPC client demo, which is the demo. Sorry, and the demo that we the first POC that we created in order to validate this work. So over here I have a C++, simple C++ application, which is going to do this work of linking at runtime the DLL, then we're getting the address of the function that we need, and then calling into this function after doing an internal trick to match the signature of the function. So we're going to see the call in here. Something that we wanted to know at this point was to actually understand which were the values that we should be providing to the functions. One like we call it. I mean, through static analysis, we saw the variables in and how the execution flow was going to be, but we didn't have an actual confirmation on which these values are going to be. So and that's where we ended up validating this work to a debugger. So on a debugger, as I mentioned on the slides, we can perform something called dynamic analysis. So the dynamic analysis is what is going to allow us to inspect the execution of this binary in memory. So we have a different tool this time in order to run this dynamic analysis process. This tool is called IDA Pro. So there are different versions of this debugger. In this case, I am using one called IDA Free, which is a free version of IDA Pro, basically. And this tool came up with the compiler tool, and also with the built-in debugger. So one can switch from this execution flow view, where you see the different execution blocks and the assembly code for a given function, to the compile view of that same code. What is amazing about this tool is that the debugger allows us to put breakpoints on the execution of the program. So if we execute the program using the expected command line in here, we can see that the program starts to execute. I have a breakpoint hit on the first available instruction on the DSW main function. Then if we go down below, we will see that there is all the parsing of the command line options that we saw a moment ago. And then there is the call to the function that we were interested in, which was SE get security profile info. So we are going to put a breakpoint in here. So if we just hit continue, the breakpoint is going to be hit, and then we can step by step continue the execution flow until this function is getting called. And from here, we can inspect the actual value for those variables. So the first one is hard-coded to 300. And then the second one is hard-coded to this value in memory, which is F1. So if we call with this value, we will be able to see that the policy information coming, returning. So let's go back to Visual Studio. So we have the Visual Studio processing here. So after some back and forth, we played with different values. We found that there is this SE key, SE area security profile flag that we can use, which with more disassembler, we found that the best value to provide with was either 35 of the requesting for the entire set of configuration policies, which is what we are going to use in here. So I'm going to change this value to this one. And then let's go ahead and compile this process. Yeah. So first thing in here is the call to log library. So yeah. So we have here the process running. And this is a utility that I use to call process hacker that I use to inspect the state of a process. So we see here that we're going to load a new library into the process. So if we continue the execution, the SCLI.dll model was loaded into test.ck, which is the binary that we are debugging at the moment. So then, as I mentioned, the function address for the function in question that was supporting the DLL was retrieved, and then that export is actually getting called with the values we provided, and that should populate a memory block that we are provided on the code. By the way, this code is available. You can look in detail later. The point here is that I want to show you that once that code is retrieved, when that call is performed, the actual profile configuration data are going to be retrieved, and that's something that we can act on. So we can export this information and have the same output that the SECI does. So just to recap, because I think I have been in a hurry. So just to recap, we got the address of the function in memory. We did a C++ trick to cast that raw address into a function pointer signature, which is this function pointer signature in here, which is something that we also reversed. So we got to understand which was the signature of that function. And then with that information, we ended up calling that function pointer with a specific set of values that we also obtained from the reverse engineering process. So among those values, there is something called the profile info. So this profile info is a raw pointer, it's a void pointer that one needs to provide to the function. And then that pointer is going to be converted or cast into a different structure called SC profile info, which is another reverse structure that we have to understand in order to be able to parse this data. Okay, let's stop this and continue the presentation because I think I'm running out of time. So, okay, we got the POC working. So we now have a programmatic way of retrieving this security configuration information. So how we can get this into osquery? Getting this into osquery requires actually following the osquery contributing guidelines. So there is a really good and documented process on how to perform this contribution. There is also a document called the LLVM coding standard that gives you the information on the coding standard used on the osquery code base. So we can follow that in order to understand how to format the code and where the guidelines have to be followed before contributing to the osquery code base. There is also an LSAC which is full of people willing to help. So I created this PR, which was merged which was merged last month. So this PR basically contained the implementation, the programmatic way of calling into the SE get security profile info API after performing the runtime linking. So having and also contain the code to use that information and expose that information through a osquery virtual table. The new table was called security profile info. And this table was merged. I mentioned that it was merged. But something that I wanted to mention here was that the most difficult part of contributing to osquery was the actual code review process. So getting people to review your code is sometimes something difficult, especially after submitting a big amount of code and then submitting a complex PR. And another interesting aspect of the contribution is that the quality assurance is something that every contributor has to be ensure that it happens in a proper way. So along with the contribution, you need to also create automated test cases and performance test cases just to make sure that your code is running as expected across the latest OS versions and all OS version 2. As I mentioned, the security profile info table was merged was merged and it's going to be released on December 22. And the version of osquery that is going to contain this change will be the version 5.7.0. And with that, I would like to thank everyone for having attended this talk. And I would also want to encourage you to push the limit of open source tools and allow yourself to contribute with new functionality to these awesome tools that everyone uses on the field. And just to finalize, we are going to see a demo of this thing working inside the osquery. So we have the osquery binary in here, the command line version of the osquery binary called osquery. So this osquery binary, what it allows us is to have access to the different tables exposed on the OS. So if we just ask for this information, we're going to see a ton of data, which are not going to be properly formatted because of the limitation of the concept that I'm using. But these are the information that we are going to get, which is exactly the same thing that Cicade will output. So if we just consume osquery from the command line and do the same thing, and now put these to osquery output 16. Yeah, then we will see this in a way better format, hopefully. Yeah, there you go. So these are the different columns exposed by this table. And we can see that the data that we need is there. And this allows us to write the security policy checks that we needed. And with that, I would like to finish the talk and say thank you to everyone.
Thanks, everyone. And thanks, Marcos, for working on this. And, I'm happy to see a talk on reverse engineering in the context of making defensive tools better, because we often talk about reverse engineering more in terms of like malware analysis and all that. So that was great.
Thank you, Ian.
Thank you very much. Excellent talk. We don't have any questions in the Zoom, but we expect some conversation and questions over in the Discord channel for your talk. So everyone knows that the speakers will be heading over there for a little while to interact with you about this talk. Thanks for the presentation. All right, we'll be taking a quick break and transitioning to our next speakers. See you in a minute.